In our last video, we saw how carboxylic acids are found in many of the common acid products that we see around us. Now, of course, the acid-base reaction isn't the only possible reaction of our carboxylic acids. So our carbonyl carbon-oxygen double bond, of course, is highly polarized towards our oxygen, creating a great electrophile here at our carbon. And then, of course, we have our electrophilic hydrogen over here, and our nucleophilic oxygen, and of course the carbonyl oxygen is nucleophilic as well, with this acting as our strongest nucleophile, and our carbon here acting as a good electrophile. The first reaction that we'll look at for our carboxylic acids is a decarboxylation, where we're actually going to remove our carboxylic acid functional group. Now, this normally requires a beta carbonyl or a beta keto. That just refers to the fact that we need a carbonyl group within 2 carbons of our carboxylic acid. Right, so if we have our carboxylic acid over here, this first carbon we refer to as the alpha carbon, and then the second carbon over here would be our beta carbon, and so this carbon needs to have our carbonyl. And of course we can have whatever carbon groups attached over here and over here. We don't really need to worry about those for the purposes of this reaction. So our decarboxylation is going to involve a cyclic movement of electrons. The first thing we want to do is rotate this bond such that our oxygen is pointing up. I'm going to draw it out like this. And so here you can see kind of our setup for this cyclic movement of electrons that I mentioned. So what we're going to do is we're basically going to be shifting our electrons around such that we end up breaking off this carboxylic acid. Right? So if I take these electrons and move them over here, and then I can take this bond and move it over there, and this bond and move it right there. So this cyclic movement of electrons here is quite similar to the Claisen rearrangement that we looked at before. But in this case, the end result, right, is that once we've moved this bond, right, so this bond is going to be broken here. We're going to be adding a new double bond here. We're breaking this here, forming a new single bond there, breaking this, and forming a new double bond there. So this is completely broken off. So now we're going to have our carbon dioxide from our carboxylic acid over here. And on the other side we have our carbon with the double bond and our alcohol, and of course our carbon groups attached over here. So again, our carboxylic acid has been eliminated from our molecule. On the other side we end up with this enol. Our enol, of course, will rearrange to the ketone, following the same mechanism that we looked at with our hydration of alkynes. Right? Hydration of alkynes initially leads to the enol, and then the enol rearranges to the ketone. So in this case, we get our carbon double bond to oxygen. We're removing this double bond of our enol. And so our ketone then would look like this, with our carboxylic acid just completely removed and no longer present. So the decarboxylation reaction allows us to remove a carboxylic acid functional group from a molecule after we no longer need it. Again, you do have to have some form of carbonyl near your carboxylic acid. This can actually even be another carboxylic acid. Right? So if we replace this R with a hydroxyl group, we can have 2 carboxylic acids next to each other, and one will then can get removed by this decarboxylation, while the other will stay. Right? Once we've eliminated one of these beta carbonyls, the other carboxylic acid is not likely to react anymore. The only thing we really need here is just to add some heat to help push this reaction forward. There's no additional reagents or anything that we need to add. The next key reaction that we want to look at for our carboxylic acids is an esterification reaction. Now, one of the things that I mentioned in the last video is that carboxylic acids are also present in a variety of compounds that we normally consider to be non-acidic. So the question would be, what's the role of carboxylic acids in those compounds? Well, in things like fatty acids, those carboxylic acids are used in an esterification reaction to link that carboxylic acid to other molecules. So carboxylic acids can do a variety of condensation reactions, which enable us to combine two different molecules into a larger molecule, which can then fulfill some specific biological role. In our esterification reaction, we're going to be taking a carboxylic acid and performing a condensation with an alcohol. So we can take any alcohol, again our R's are just representing any given carbon chain, and we can link those together to form a new functional group that we call an ester. So we take the oxygen and the carbon from our alcohol, and we're replacing our hydroxy group from our carboxylic acid in this final product. This reaction will require an acid catalyst to help to push our reaction forward. Again, we can classify this as a condensation reaction. We also will call this a nucleophilic acyl substitution reaction. So the acyl group refers to a carbonyl with a carbon chain attached. So we're substituting what's attached to our acyl group, right? So our nucleophiles are getting substituted at the acyl group. We're starting with our hydroxy nucleophile, and we're replacing it with a alkoxide nucleophile with that oxygen attached to our carbon chain. So this is our first example of a nucleophilic acyl substitution. Let's walk through the full mechanism of this esterification reaction. So we're going to start with our carboxylic acid. Again, remember our key reactive sites on our carboxylic acid, our nucleophilic oxygens, and our electrophilic carbon. This reaction is going to share a lot of similarities with the nucleophilic addition reactions that we saw with our carbonyls previously, but we'll have some key differences due to that extra hydroxyl group here. So our first step is going to be protonation of our strongest nucleophile here, right, our carbonyl oxygen. So we're going to come in and take a proton from our acid catalyst, and now we get our protonated carbonyl. At this point now we can attack with our nucleophilic alcohol. I'm going to show ethanol in this case. As we bring that into attack, as with our other nucleophilic addition reactions, we're going to move our electrons up onto that oxygen at the same time. So that leads to our product here, our intermediate rather, where we have our alcohol now up here at the top, and we've got our new alcohol connected on down here at the bottom. And of course this will have a positive charge. Notice how we get this key tetrahedral intermediate here in this reaction mechanism. As we'll see, this is fairly common. We're going to be looking at other nucleophilic acyl substitution reactions in our upcoming lectures. And this sort of tetrahedral intermediate is a very common intermediate in our nucleophilic acyl substitution reactions. Now at this point we need to deprotonate this, so I'm going to use the water that formed from my acid catalyst, and I bring in that water molecule and I'm going to remove my hydrogen here. So I've got my alcohol and my new nucleophiles now attached here without my positive charge. So at this point, we've essentially, again, followed exactly what we would do in a nucleophilic addition reaction to a carbonyl. So at this point, it's kind of similar to the hemiacetal that we would see when we're adding on an alcohol to a ketone or an aldehyde. But now, because we have that extra hydroxyl group, in the second step, or the second phase of our reaction, we're going to end up removing that hydroxyl group instead of adding on a new alcohol. So the first thing we're going to do is we're going to bring our acid catalyst back, and we're going to protonate our hydroxy group here. So we're going to form an alkyloxonium ion, where we then have a good leaving group. So we've got our good leaving group here. We have our nucleophile that was attached over here. Now we can do an elimination of this water. So this is going to be kind of like a E1 reaction. We're going to bring down our electrons here from our oxygen and kick off that water molecule. So now we have just our alcohol nucleophile attached. We've got our double bond now again of our carbonyl. And then to get our final product, we just have to use the water molecule that just left to deprotonate here. So we bring in our water molecule, deprotonate this, and of course we're also regenerating our acid catalyst at the same time here. So we reform our carbonyl, and now we have that ester product. So once again, we've taken our carboxylic acid and we've just replaced that hydroxyl group with our alcohol. All right, so this portion of our molecule over here is from the alcohol, and of course this portion of our molecule is from the original carboxylic acid. So we refer to this as an addition-elimination mechanism with a tetrahedral intermediate. Right? So the first step was essentially, or the first few steps were a nucleophilic addition. Right? So this is our addition portion of the reaction. And then of course the second half of our reaction was a elimination portion where we were breaking off our original hydroxy group to get that final product. So it's addition to get to our tetrahedral intermediate here, where we have our four groups all bonded to that carbonyl carbon. We eliminate our water to get our final ester product, where we just have our carbonyl and now that new alcohol added on. Now, of course, our ester, as you'll see, has a lot of similarities to our carboxylic acid. Right? The only real difference between an ester and a carboxylic acid is that instead of that hydrogen, you have that extra carbon on there as well. So we refer to this ester as a carboxylic acid derivative. All right, it's made from our carboxylic acid, and it does have some similar properties to our carboxylic acid due to the similarities in structure there. So we're going to be looking at some other examples of carboxylic acid derivatives in the next few lectures. There are actually a lot of different compounds that we can make from our carboxylic acid using similar condensation reactions. They'll all have some key similarities to carboxylic acids, but also some differences, since of course all of them will be lacking that acidic hydrogen there on our carboxylic acid. The esterification reaction and our other nucleophilic acyl substitution reactions that we'll be examining in our upcoming lectures are incredibly important reactions for us. So as I mentioned, our fatty acids will contain the carboxylic acid functional group. Within our body, though, our fatty acids will be stored in larger molecule conglomerates called triacylglycerides. What we'll do is we'll actually combine carboxylic acid with an alcohol. So we're going to use a trial actually that will link three fatty acids together into one larger molecule. So in that way we can then have a very efficient mechanism of storing those fats in our body, because instead of having tons of different little fats all floating around, we can link them together into these larger molecules that we can more easily store in our body. So these sort of reactions are really critical for our body. They enable us to easily add units together to make larger molecules, and this reaction can also be reversed, so we can break it apart to release those individual molecules later as well. So in our next few lectures, we're going to be looking at a wide range of different nucleophilic acyl substitution reactions that we can use to make varying carboxylic acid derivatives, and we'll also look at how we can reverse these reactions and bring it back from our esters or our carboxylic acid derivatives to our carboxylic acids. Right, so these are our interchangeable processes where we can convert between our carboxylic acid and our different carboxylic acid derivatives. And so we can actually carefully control whether we want to build up larger molecules or break it apart into our smaller molecules and release that acidic carboxylic acid functional group.